Hello, my name is Ryan McCloskey, and in this presentation, myself and Colin Fardey from the AR/VR team within the MEPS unit at TSSG will give you an idea of what VR can do for you and your projects, as well as giving an overview of the VR content creation process. To start things off, just a quick overview of the AR/VR team itself. We're a small sub-team within the MEPS unit at TSSG. There's currently 5 members, and we specialize in augmented and virtual reality application design and development. We have a mixed reality lab at ARC Labs, which is currently nearing completion, and that was funded thanks to a grant from the Enterprise Ireland Capital Call. So we have a variety of equipment such as VR headsets, AR equipment and such available. Next up, we'll give a quick look at our development process that we use, which can vary depending on projects, but this will give a good idea of how we work. The VR development process can be boiled down to 4 main steps, and that starts with storyboarding. So this means that we will draft our initial requirements, decide what we're going to use, how we're going to use it, depending on the needs of the project itself. So we define the use for the application, we create some storyboards to aid in the planning processes for development, and also we select our development tools, which are going to be used throughout the project. Next step then is asset creation. So depending on the time, the budget, the complexity of the project, we will either create assets in-house or we will source them externally. So any assets that are created in-house, they can be done either by hand or using a combination of photogrammetry, which Colin will speak about later, and manual editing process. Next step then is physical development. So this means that we will start building the application within the selected development tools. So for VR development, this is generally either Unity or Unreal Engine. So we use a lot of custom interactions which can be repurposed for any VR application. So this can include hand interactions and stuff of that nature, which we'll show a little bit of later on as well. So development itself is a multi-step process, and that involves interaction setup, content integration, which integrates the assets from the previous step, and we also define our application logic. And the final step, which runs in tandem with step 3, is testing. So testing is done throughout the development process. We will perform testing either within the AR/VR team itself or in collaboration with the PSS unit for larger projects. So we perform rigorous testing to ensure that all our output is accessible, and that's very crucial for VR development. Because VR is such a new technology, there isn't quite a standard method of interaction just yet. So a lot of our work goes into prototyping interactions and making new interaction systems. So sometimes this goes quite well, as you can see in the examples below, and other times, which you'll see in the next slide, it does not go so well. Interaction prototyping is not a faultless process, so at times it doesn't quite go as planned, as you can see in the video playing on screen now, but all of that helps towards getting to the final stage where we have good interactive systems which can be repurposed across multiple projects. Next up, we'll go through a project that was completed by the AR/VR team earlier this year, and that's our COVID-19 information app. The app itself is available for the Oculus Quest at the link displayed on screen now. So the idea behind the application is to bring information about the COVID-19 pandemic, and in particular the lockdown that was ongoing at the time, bring that to virtual reality and essentially bring education to VR and show exactly how VR can be of benefit to providing information to the general public. And in the next slide, we will have a quick look at the project itself, its final output. We'll just display a video on screen and you can see what the app is about. This particular project was a very good example of the implementation of our development process. So you can see where we went from our initial storyboards all the way to the very end of the project, its final output within the VR application. So over the course of the next couple of slides, we'll go through the steps that we went through for the process, how we got from start to finish on the project itself. The application itself is essentially three main scenarios. First, we have General Information Hub, which will give accurate information which has been collated from info given out by the HSE. We have it displayed within a 3D virtual environment which you can explore and interact as needed, combined with some custom-made videos to explain the situation as well. Second up, we have our hand washing scenario. And the hand washing scenario is essentially a interactive scenario with a number of flashcards for users to interact with, and the goal is to organize the flashcards into the correct order. So the cards themselves represent the 10 steps of correct hand washing, and the idea behind this is that hand washing is a process that is not always done correctly, and we needed a way of explaining it properly so that it can be fully understood and implemented by anyone who uses the application. So we tested a couple of different methods of interaction for the hand washing scenario. So in the end we decided on flashcards because the main reason being that the VR interaction is not quite there yet in terms of offering a accurate measurement of is the user doing this or that correctly for fine movements such as hand washing. So we decided that the most accurate and the most understandable method of interaction there was the use of flashcards, and this all ties into our overall goal of accessibility for everyone. So next up is the social distancing scenario. And social distancing is a concept that a lot of people at the beginning of the pandemic had a lot of trouble with in terms of understanding what it was and what exactly it means for them, and even having trouble with spatial awareness in terms of how close am I to this person and that sort of thing. So the problem with that is that you can't really practice it in a live environment without potentially causing danger to yourself or to others. So in that situation, VR is perfect because VR offers a full-scale 3D environment where you can practice social distancing, but you're not causing danger to yourself or to others. So because it is proper full-scale, 2 meters within VR as it's designed here is 2 meters within the real world as well. So what we decided on for the social distancing scenario was a retail shop environment that anyone would be familiar with, and the goal is to navigate through the shop and stay the correct distance away from the other people that are in a queue as well. So initially for the locomotion, we tested a couple of different methods. We looked at smooth locomotion, but the problem with that is that some people do experience motion sickness when using smooth locomotion within VR. So keeping with our goal of accessibility, we decided to go with teleportation, which we found works perfectly fine for our needs here. So again, just because VR allows the use of real world scale, it's very important that that's used to create the distance association, which is very important to practicing safe social distancing. And here we have just a quick look of the end result of the social distancing scenario, where the user just navigates their way through the environment, and the goal is to just get through the shop and get out of there while maintaining the correct distance. So next up, we're going to move on from the COVID-19 project, and we will hand things over to Colin, who's going to explain the photogrammetry process.
The technology of photogrammetry has been around for quite some time. Ian Dowman first proposed it in 1984 as a way to map topography of terrain using satellite images and satellite data. Photogrammetry is basically the process of measuring distance. It is the appliance of geometry and mathematics to make measurements and extract 3D data from photographs. So it essentially takes photographs of an image and recreates what's in the image in geometry form. The idea is to take as many images as you can of an object if you wanted to convert it into actual geometry that can be used in an application. The photos are then rearranged and stitched together by the software, and eventually it will give you a 3D representation of the object you've been taking pictures of. So one of the benefits for the photogrammetry pipeline is there is a wide availability of softwares, and the majority of which are free. And as you can see from this slide, Autodesk make one, Reality Capture, Meshroom, which is totally free and open source. So this is useful for any budget on a project. As I said before, it's not for every project, and the process itself can be quite involved. It needs to follow a very specific path. And in this slide, you can see the process that needs to go through to finally make its way into an application. So the first step would be image capture. So that means you capture as many images as you can of the object you want to turn into geometry. The more photographs, the better. And the second step would be image processing. So that's all the recorded images are transferred into the appropriate software, and each image is processed and stitched together. And the next phase of the process is creating a point cloud. So all the images that have been stitched together and analyzed, they come out in the form of a point cloud. A point cloud is basically a position in space that has color information, scale information, and so forth. That point cloud information is then converted into geometry and can be exported to a 3D package, an external package like Maya. The geometry produced from the point cloud is very dense and in most cases is unsuitable for use in an application, especially a real-time application like a game engine where the application will run. So it then needs to go through a process called retopology, where new geometry is drawn over the high-resolution, high-detailed meshes. Then the detail from that mesh is projected onto the low-resolution geometry. So this makes it easier for the real-time application to process everything, so there's less to compute. The final step of the process is getting the geometry produced from the photographs into a game engine. So it's textured accordingly and taken into an application like Unity or Unreal, where it'll be used in the final application. On slide 17, you can see a snapshot of the process. So each white dot in that image surrounding the object is the position of the camera, and that is the information that the computer uses to reconstruct the object. So on this slide, you can see an example of a point cloud. So this is just to further illustrate what a point cloud is and what it does and why it's useful. So a point cloud is just a set of data basically, and it is represented in points. It's got an X, Y, and Z coordinates. Just depicts the location in space of the object that you're trying to photograph and turn into geometry. As you can see here, this is someone trying to reconstruct a plant. And on this slide, you can see an example of a high cross, which was produced using the methods talked about in previous slides. This was scoped out for a project in maps that we were working on. But in its current state, it isn't usable. It's way too dense of a mesh. It's poor for optimization of applications that run in real time. So it's going to have to go through one final stage, and that's the retopology stage. As you can see, it's a good way of capturing all the color information, all the correct color information, and all the correct forms as well. So in this slide, you can see the process of retopology. So new geometry is drawn onto the high resolution mesh. That blue wireframe you can see is the actual lower resolution mesh. It's hand drawn, manually drawn on top of the high resolution mesh, and it basically just has to match the silhouette and the shape of the high cross. Photogrammetry might not be the ideal solution for all projects, but it can be helpful to get a head start. Some of the issues that occur with it are things like artifacts or mesh artifacting. So you can see by the image that some of the details are missing. This normally happens when the software doesn't interpret the data correctly, or there just simply isn't enough information for it to do that. It also produces baked lighting. So the lighting that's present when the photographs are taken is the lighting that you're going to get in the mesh, in the textures, and in the detail. This isn't always what you want, as it's running in a real-time application, and you probably want the lighting to change according to the lighting in the scene. And as mentioned before, it does produce high resolution meshes and high resolution textures, which neither of are ideal for running in real time applications and can be very computationally expensive. And that's all for me. That was the process of using photogrammetry in the AR VR development pipeline. I hope you found it educational, and if not, I hope you found it somewhat interesting.
So just as a quick example here of how AR and VR can be implemented into existing projects, it can be particularly useful as part of dissemination activities. So it can add an immersive dimension to the project output. It gives you a 3D interactive representation of data, gives you the possibility of integrating live data into demo experiences, and particularly it offers a visualization of results that can reveal information in a far more accessible manner than simply just showing info on a graph, which may not be understood by anyone. VR has applications across many industries, so you can look at science, healthcare, manufacturing, agriculture, and many more. Across many industries, VR is already being used as a training tool for new employees so they can get to grips with what they need to do in a virtual environment as opposed to a real world environment where they could cause damage to equipment, machinery, or even themselves. So virtual reality can be a very good tool for that sort of thing. And that's about the end of our presentation today. So hopefully you'll have seen here how VR can help with existing projects that you may have ongoing, anything new that you may have in mind. At the moment, it's currently in its infancy, although it's growing fairly quickly. So we're seeing over the course of even the last couple of years where any particular limitations that VR does have, say in terms of screen resolution and such, they're quickly decreasing, and we hope to see that continue over the next couple of years where we can fully see the potential of the technology.